Okay, so for homework, you were doing solving differential equations. And so now we're doing the next bit, which is modeling with differential equations. So forming and solving the differential equations. So we've done all this bit here already. We know how to do all this bit. We know how to eliminate the constants. So we're moving on to forming differential equations. I'm going to hand out some sheets so that you don't have to worry about writing it down. I've got the paper. I don't know, we've got two sheets of the same there. I've got two sheets of the same there. You should have two sheets. The first one should start with the amount of light, and then the second one should start with putting it all together. Okay. So, right. So the first thing we want to do is forming differential equations. So we've already learned how to solve a differential equation when it's already been given to us. But now we want to learn about forming differential equations and modeling a situation using a differential equation. So we're going to start by defining our variables. And mostly that will mean we only need two variables. We need to decide what are the two variables that we're interested in that question. And more often than not, one of the variables is time. But watch out, because that means that on those few occasions where time isn't one of the variables, you can make a mistake and accidentally think that time is a variable, because it is, 85, 90% of the time it is. And if possible, we want to state the units for each variable. Okay. Rates of change. Well, we already know this. The rate of increase of y with respect to x, we would call that dy by dx. So dy by dx, we know, means the rate of increase of y with x. If instead I said the rate of increase of y with time, then that would be called dy by dt. Not with x, but with time. Fine. Okay, the rate of increase of height. Sana, your little brother, last time I saw him, he was only that big. And now he's grown that big, and it's only a week later. Wow, he's growing so fast. What is it that's causing him to grow fast? Just time. It's just over time that kids grow. Although if he's growing that much a week, we need to really work out if there is some sort of growth hormone problem or something like that. So the rate of increase of height, when we don't say what's causing the increase, you can pretty much bet it's going to be time that's causing. So this would be dh by dt. Time is like a variable that's constantly running in our work. So we're always thinking about time as being a factor in things. This is slightly weird. The rate of decrease of y. Well, that's not a good value. The rate of decrease of y with x. We're going to rewrite that. We're going to write that as negative dy by dx. And this negative is showing that the gradient on that graph is downhill. The negative is showing the gradient on that graph is downhill. Now, strictly speaking, if you didn't put in the minus in there, it would kind of sort itself out anyway. But there's a reason why we put the minus in there, and that'll become apparent later on. We're also going to get a constant, and we want that constant to be positive. So by putting in the minus in there, we can make sure that constant will be positive. But we'll learn about it a little bit later on. How would you write the rate of decrease of y? Apart from that to good.
minus dy dt.
Yeah, perfect. Okay, how would you write acceleration? What is acceleration? How would you write it? And we want to write it in this form, d something by d something. How would you write acceleration, Roger?
dv by dt.
dv by dt. The acceleration means your velocity is changing with time. That's what acceleration means. Rate of change of velocity. All right, then, that's how you'd write acceleration. How would you write velocity, but as a rate? After that to Matthew. Oh, look at me. I'm running at a speed of 10 miles an hour. What's changing?
Speed.
No, my speed is 10. It's not changing. Oh, look, I was near the table, but now I'm running away from the table. My direction isn't changing. My distance from the table is changing. So velocity is rate of change of displacement, dx by dt, or ds by dt, depending on whether you want to use s for displacement or x for displacement. Okay, and then now I'm harping back to something we learned in GCSE maths. The rate of increase of n, we know, is dn by dt. Now it says the rate of increase of n is proportional to n. And so this is to do with proportion. And that's something from GCSE maths. And we learn in GCSE math, if somebody says y is proportional to x, we would write y, and then we'd use this symbol here, is proportional to x. But then a second later, we'd write y equals kx. So this sign means it's proportional to, but you can also replace that sign with an equals k. So y equals proportional to x, we would write as y equals kx. We're going to skip that step. Not going to bother with that. So we'll just write y equals kx. Y is proportional to x. And the other thing they would say is y is inversely proportional to x. So y is inversely proportional to x. In GCSE, we would write it like this. Y is inversely proportional to x. So inversely proportional to x means proportional to 1 over x. And then we would rewrite that as y equals k over x. And again, the proportional to sign just changed into an equals k. So it's the same rule again, the proportional to sign just changes into an equals k. So if we're doing this, the rate of increase of n is proportional to the current amount of n. The rate of increase of n would be dn by dt. Is proportional to, we'd write as equals k. And what's it proportional to? Well, it's just proportional to n. So that's that differential equation form. And actually, we're going to see this a lot today. This same differential equation, this particular one. We're going to see that a lot. We'll see others, but we'll see this one quite a lot. Next one. The rate of increase of x is proportional to the square of x. Sana? Lovely. The rate of increase of height is proportional to the difference between h and h max, where h is a constant. Roger?
dh by dt
Max minus h. Lovely. The difference between h and h max. The difference between h and h max is the subtraction. h max minus h, and then it is proportional to means k times that. The rate of decrease of m is inversely proportional to m. Here?
dm by
Almost. Yeah.
oh minus dm.
Minus m by 2. Of course, if you didn't use the minus, the k would just appear with a negative number in it. We want the k to be positive. We want our constant of proportion to be positive. So we'll see that later on. Rate of increase of r is inversely proportional to the product of r squared and h. Good.
Over r squared h.
Perfect. The rate of decrease of p is inversely proportional to the square of p. Matthew?
Minus 2p
The rate of decrease of y is inversely proportional to the square root of y. Right?
minus u by h
Lovely. The rate of decrease of p is inversely proportional to the product of p over n and q over n, where q is n minus p and where n is a constant. It looks very like wordy and complicated, but it's no harder than any of the other ones we've done. It's not any harder than the ones we've just done. Anna? Yeah. And the n's, you can multiply them together so you get n squared, and that will end up on the top of the fraction. You know the rule with when you're doing fractions. So that's equal to kn squared over p times n minus p. Kn squared over p times n minus p. Okay. Acceleration is proportional to weight minus velocity. The others all say rate of something, but this one doesn't say rate of anything. But we know that acceleration is a rate of something with respect to something else. Roger? Yeah, we might want to replace the W with mg because it's probably the case that we know the mass. And so you might want to replace it with mg, or might just want to leave it as that. Velocity is inversely proportional to distance from starting point. Velocity is inversely proportional to distance from starting point. Good.
ds by dt equals k over
What does S stand for?
split.
And that's the same as distance from starting point. if somebody explains to me some rule, like any of these rules here, they give me some sort of a theoretical appraisal of a situation, I can form a differential equation, and that differential equation can then model that situation. So it's really powerful. When grey squirrels are introduced to the UK, they thrived. The population grew exponentially, but there will always be an upper limit, let's call it L, to the population that any environment can carry. Why? So we talk about human overpopulation. We talk about human population because as the population of humans increases, two things happen at the same time. One is the amount of food we need grows in proportion to how many people there are. So there might not be enough, space to grow all that food that we need. And also the amount of waste that we produce increases exponentially. And that waste is often a cause of toxicity either to us or to the environment. We're talking about plastic pollution in the form of humans. We're talking about carbon dioxide pollution in terms of the warming of the atmosphere. These are things that, but with like squirrels and stuff, they don't do that. They don't drive cars. They don't do anything like that. But they do produce a lot of excrement. So with mice, when the number of mice increases a lot, then the amount of excrement increases a lot, and then diseases increase a lot, and so some of them end up dying. And with squirrels, they're probably not, their numbers are never going to get that big as a mouse population would do. But of course, squirrels need to eat, and they need to eat over the winter. They need to bury things that they can eat over the winter, and they need to bury nuts and stuff like that. And if there's loads and loads of squirrels, there might not be enough food to go around, and some of them might starve to death. So there's a limit to how many squirrels the population can support. So if there was no limit, I would say our model should just be a simple model. If there was no upper limit, then I would just say our simple model would be dn by dt. N is the number of squirrels, and t is the time. dn by dt equals kn. Why? Because the more squirrels there are, the more babies they'll have. And so the rate at which the population will increase will depend. That's why if you've got a population that's almost extinct and there's only like one, dodo left, then they're stuck because there's no one for him to mate with. And so he's not going to have any babies. And so that's it. That population is doomed to decline, to become extinct. So here we've got dn by dt equals kn. But this will produce this type of a graph. It will produce a graph like this, n, t. I don't know, let's say today there's, 100 squirrels. That population will just go on and on and on, and that has no limit, that graph. It will go up to 1 million, it will go up to 1 billion, it will go up to 100 billion. That's not a good model because you can't have 100 billion squirrels in Harrow. There's just not enough nuts for that many amount of squirrels. So what we need to do is we need to adapt this equation, and we need to adapt this equation so that as we get near to L is just a constant, it's not a variable. As we get near to L, this rate starts to slow down. So we want this to drop near L. So we're going to have to improve this model a bit. What do you reckon we can do? Something simple that we can do to improve the model so that when we're near like 1 or 2, near 10 or 20 or 1 or 5 or something like that, then it's still this equation. If you're at a small number of n, it's still this equation. But if you're at a large number of n, then it has to go more to dn by dt is closer to 0. So how could we fix that? Just multiply it by something. I know. Multiply it by L. Oh, no, that's no good, is it? Because if you multiply it by L, L might be, I don't know, 1 million. That's massively changed the formula when n is small. Okay, that's not very good. Okay, multiply by something more complicated than that. Let's use the brackets. Let's multiply it by what about multiplying it by L minus n? What about multiply by L minus n? Well, that works a bit better because L minus n, when n is 0, that would be, well, that would just be L. When n is 0, 1, 2, 3, it would be approximately n. So when n is small, that will be approximately the same as, and when n is large, then it's going to become, well, when n is large and close to L, that's going to become, well, roughly 1. So, so that's going to become, yeah, so it's going to be L minus L roughly, so it's going to become 0. It will be approximately 0. So it kind of fixes one problem. It kind of fixes one problem, which is that it this multiplier, when n is large, L minus n, when n is close to L, L minus n gets to 0, and so this rate will go to 0. It doesn't fix the problem that we had when we just multiplied it by L a second ago, which is when L is small, it gives you, when n is small rather, it gives you kn times L. I didn't really want to multiply the kn by L. So what I might do is now divide it by L. I might divide it by L, see if that fixes it. So now, when n is, you know, close to 0, that's going to be roughly L, and that's going to be kn times L divided by L. So that's going to be kn, how it was originally. Now, when n is large close to L, that's going to become roughly 0, and so that's going to make this whole rate get very close to 0. So there you go. All I did was I started off with a situation, and I said, look, I want to model this, and then just by playing with the equation, I created a model for it. So once you've created a model for it, once you've created a differential equation to model it, then we'll be able to do the rest of it no problem. So you can do loads. Okay, so now we're doing other situations. And in each one of these situations, we've been given somebody's idea of what might be going on here. So we've got a boy is suffering from a bowel infection. Number of bacteria feasting on his intestine is increasing. The doctor says the rate of increase of bacterial population is proportional to the number that are present there. So this is the thing that the doctors told us, and we have to use that information to help us form our differential equation. So the doctor's given us that bit of information. We need to form our differential equation. On your sheet, that question's there. On your sheet, that question has got numbers on it, although the numbers are being blanked out, because what we're going to do first of all is we're just going to write the differential equation, then we're going to come back to them and use those differential equations. So we're going to do it in 2 stages. So you can start writing on it now, because we're already starting with the question, but you won't be able to fill it all in. So leave enough space because we've got more to add to this. We need to define our variables first. So n is going to be the number of bacteria. I'm guessing that's going to be in millions, although it's probably actually not in millions, it's probably in like hundreds of billions, but never mind. And t is going to be time. Again, I don't really know, so I'm guessing that's going to be, say, hours or days. Okay, so there's my definition of my variables, and I've given them units, even though I just kind of wasn't sure what the units were, I just made something up. Now I need to write this as a differential equation. Write this as a differential equation for me, Sana. Lovely. That's it. We formed our differential equation. This is going to come up a lot. I already told you that. This is going to come up a lot. It's the exponential growth differential equation. It's the standard exponential growth differential equation. That's going to come up a lot. Next one. The amount of light measured in lumens in a rainforest decreases in proportion to the square root of the distance below the tree canopy. Okay, so here's our, let's make it a bit smaller. Here's our rainforest. Here's our rainforest. This is the tree canopy. This is, you know, sort of the height at which all, you know, the tops of the trees are. So somewhere about there. It might even be a little bit higher than that. Probably need to move it up a bit. Where the tops of the trees are. And what they're saying is, if you measure the distance below there, so if you measure a distance below there, and we'll call that distance x. If you measure a distance below there, x meters below there, then according to the thing that I can now no longer read, the amount of light measured in lumens decreases in proportion to the square root of the distance below the tree canopy. So we've got sunlight here, lots of sun rays here above the tree canopy. When you get down below the tree canopy, the amount of light gets less and less. You get less light the further down you go because the leaves are all blocking the light. So there's not much light at the bottom of a rainforest. We know that. Okay. So we're going to define L as amount of light in lumens, and X as the distance below the top of the trees in meters. And this is not to do with time. This is nothing to do with, oh, it's getting late, the light levels are falling because it's dusk. This is to do with every day at midday, there isn't a lot of light. There should be a lot of light at midday. There isn't a lot of light at the bottom of the tree canopy. But as you go further up, at the bottom of the rainforest, as you go further up into the tree canopy, you'll get more and more light. And if you manage to climb right to the very top, you'll have tons of light. Let's form that differential equation. Roger. Should I make that a bit more legible? The amount of light measured in lumens decreases in proportion to the square of the distance below the tree canopy.
Minus dl by dx.
Minus dl by dx.
Equals
It wasn't dl by dt, it was dl by dx. It wasn't the time that was causing the light levels to fall. It was how low you are from the tops of the trees, how much you've dropped below the tops of the trees that's causing the light levels to fall. To make bread, you add some yeast to some flour and stuff and leave it in a warm place. Normally I look up the stuff, I just couldn't be bothered this time. I don't know how to make bread, but I know it's something to do with yeast, that's kind of all I know. We're going to define N as the number of yeast cells. I'm guessing it's going to be in millions, but probably even more than that. Probably much higher. T is time. I'm guessing that's in hours. I know you have to leave your dough to rise for a few hours or something like that. Okay. Form the differential equation for that. There.
dn by
It's the same one as we had with the little boy and his bacteria. It's the same differential equation. That's the exponential growth differential equation. It's going to come up a lot. We're going to see it a lot. As soon as we see this, we're going to shout out exponential growth. So we know that. We'll be familiar with it. A tree stump is rotting. So you've got this tree here. And it's a lovely tree. It's helping to absorb some of the carbon dioxide from the global warming that we're producing. But for some reason, you decided to chop it down. You've chopped it down. You've cut it here, and you've chopped it down. And that's it. Tree stump, left, tree, gone. The tree stump, well, the stump is probably the bit that you see above ground. But actually, it all extends below ground. There's all the tree roots and stuff like that. And all of this stuff that's left here, now, well, you've chopped off the tree, you've chopped off the leaves, so maybe it will die. Maybe it will die and it will start rotting then. So it'll start rotting. The mass decreases at a rate proportional to the amount of stump left. So we're going to say M equals mass of stump and T equals time. I'm going to measure time in quite big interval this time, years, because tree stumps don't rot quickly. You'll be waiting years for it to disappear. Mass, kilograms. Form the differential equation for that. Drew?
dm over dt.
Yeah, well done.
Equals km.
Yeah, that's not the same. It's almost the same, but it's not the same. It's got the minus at the front here. And that makes it, that completely transforms it from an exponential growth equation to an exponential decay equation. This is our standard exponential decay equation. Again, it's going to appear a lot today and in our homework and stuff like that. Radium is a nasty radioactive substance that will kill you. If you have some radium that you need to get rid of, don't worry, it will decay over time. A sample will lose mass at a rate proportional to the mass that's remaining. M equals mass. Let's imagine you've got a lot of it, a kilogram of it would be quite a lot. And T is time. I'm guessing it's not going to decay that quickly, so I'm going to measure time in years. For my differential equation, Matthew?
Minus dm dt.
Do you recognize that? It's identical to the last one. It's identical to the tree stump. It's the same situation. Of course, they won't be identical. For instance, the K here is likely to make a big effect on how quickly the stump decays into something that's, is no longer detectable almost. Whereas the different value of K here is going to make a big difference into how long the radium hangs around for. Newton didn't just come up with the 3 laws of motion. He also discovered the law of heating and cooling. He said a cold liquid placed in a room at 20 degrees C will gain temperature at a rate proportional to the difference between the liquid and its surroundings. So the cold liquid, obviously, everyone knows, is Coke. So you've got a glass of Coke. Here's a glass of Coke. And it's kind of a black liquid, isn't it, Coke? Black liquid in here. And it's really cold. It's really cold. It's you just taken it out of the fridge. Maybe it's 3 degrees. Maybe it's 3 degrees. 3 degrees C. But the room isn't cold. The room is hot. And so the room is at 20 degrees C. And so what is going to happen is the heat is going to sort of penetrate into there. And although the Coke was lovely at 3 degrees C, by the time it gets to like 15 degrees C and it becomes warm, it's not so nice anymore, is it? It's like disgust. Coke is such a nice drink when it's cold, and as soon as it's warm, it's totally undrinkable. It's absolutely revolting, isn't it? All right? I mean, you look like you like warm Coke. Or you don't drink Coke at all.
No, I do.
Your generation, actually, you've stopped drinking like fizzy drinks and stuff like that. You kind of just drink water, don't you? And like healthy things and stuff like that. We lived on Coke. We grew up on Coke. Mena's brother, he passed away last year. He would drink 3 cans of full Coke a day. And when you go around to his, and he drank warm Coke, by the way. He didn't like his Coke warm. So when you went round to his house, he'd always offer you a Coke, and I'd always be tempted. If you only drank full Coke. I have full Coke maybe once a year, if it's my birthday or something like that. I'll treat myself to a full Coke. It is my favourite drink. It's so nice, but it is so bad for you. There's so much sugar in it. So a cold liquid place will gain temperature at a rate proportional to the difference between the liquid and the surroundings. So when it's 3 degrees C, there's quite a big difference between those two temperatures, isn't there? The difference would be like 20 minus 3 would be 17 degrees difference. So the heat's really going to pile in there because of the difference. But after a while, it's warmed up. It's no longer at 3 degrees C. It's now at 13 degrees C. That's not such a big difference anymore. And so you're going to find that the heat doesn't pile in there quite so quickly as it was before. Oh, that means water, doesn't it? Okay. So the heat isn't coming in as quickly anymore. Okay, let's form a differential equation. They've told us to use theta for the temperature of the liquid and T for the time in hours. So they've already defined the variables for us. I think they're trying to stop us from accidentally using T for the temperature of the liquid and T for the time, because even if you use a capital T for the temperature of liquid, it still can easily get confusing and mix up. So these are the variables that we're going to use. Can you please form the differential equation for me? Asking that to Sana. D theta by dt. Okay. 20 minus theta. Perfect. This bit here is the bit where you're working out the difference between the room temperature and the temperature of the liquid. And then once you've done that, you just do it proportional to that. So yeah, lovely, good. We measure radioactivity with a Geiger Muller tube. So let's say you've got this nice sample of uranium here, which you brought into class to show everyone. It was a gift from your dad who went to Russia, and he brought you that piece of uranium. And you've got your Geiger Muller tube. So there's your Geiger Muller tube, and it's attached to a counter. And when you put it near to here, when you bring it near to here, you get a huge count rate on this meter. I don't know, 150 or something like that, yeah? 150. It goes, have you ever heard it? It goes like, you must have heard it, Geiger Muller. I don't know if they use it. Do you use one in school anymore? You have like some radioactive isotopes in a little jar, and then your teacher pulls them out and says, let's see how much radioactivity is coming out from there. Don't do that anymore. I really did that a lot. Most of us have died with cancer since, so probably that really bad. So now what happens if you take your Geiger Muller tube and you put it away? You move it away to somewhere else. I don't know, even move it out of the room. Move it into a different room. Does the count rate recorded on the meter drop to 0? Matthew? Why? It's background radiation. These walls, this floor, this ceiling, all the building materials around us, all the rocks around us and building materials have some radioactive decay going on. And so you won't get an answer of 0. You'll get an answer of, I don't know, 10. It's not big. Don't need to worry about it. Don't go home and cry to your mum and say, look, mum, the teacher told me that there's loads of background radiation around and we're all going to die. It's not that bad. It's not a huge amount. So the count from there, if you take it away from there, you're going to get a count of 10. So if you're now working out in your brain, how much of the count is actually coming from our uranium sample? How much is actually coming from the uranium sample? Yeah. When I take it away from the uranium sample, point it completely miles away from it, it still gives me a count of 10, background radiation. When I point it back to the uranium sample, it gives me a count of 150. How much is coming from my sample? Yeah, obviously. Okay. Right, now, so there's 140 is coming from here, and 10 is coming from just the background radiation. What's going to happen to this number in a few months or in a few years? What's going to happen to that number over a few months or a few years? Good. The one from here.
Or decrease.
Decrease, because it's decay. There'll be less of it left. What's going to happen to this one over a few months or a few years? It doesn't really decrease. Okay. The background radiation is from like huge stuff, which is, I mean, it'll decrease over millions of years, but it won't decrease over a few years or a few weeks or a few months. So this is going to stay the same. This is going to stay the same. Oh, it's done that thing where it dies again. You know what we can do when it dies? Sometimes just like talking to it nicely convinces it to start working again. What sort of a rubbish program is this? I don't want it in class, so I have to go back onto it. It's not going to behave. Okay. No, I don't want the crash recovery. Equation for 1 plus. Okay. Oh, I need to set the thing back onto record, don't I? We've lost my lovely diagram of the Geiger Muller tube. I won't be able to recreate it. It was a work of art, that one. Okay, so what's going to happen here is your uranium sample, it's 150 today, but next week it'll be 148. And a week after that, it'll be 146. And then a week after that, it'll be 145. And it's going to decay all the time. Whereas the background 10 is not going to decay at all. This is not going to decay. So, okay. C equals count and T equals time. I don't know what units to put in here. This is becquerels and this is, I don't know if it's hours or weeks or years. It depends on what my radioactive sample is going to be. I'm just going to leave them as blank. Okay, anyway, can you form my differential equation for me, Michael?
dc by dt minus dc by dt equals k times C minus 10.
Yeah, C minus, well, whatever the background is. If we know what the background is, you know, C is a variable. It's this variable here. But B is the background, which is a constant, whatever it turns out to be. We don't know what it is at the moment. I made up the number 10. I made up the number 100. But did you see how Raja did it? He said, look, I know what's going to be decreasing. It's going to be not the 150 that's decreasing. It's going to be the 140. The 140, which is the 150 is the total count, out of which 140 is from this and 10 is from that. So that 140 is the thing that's going to be decreasing. So he realized that any count that you read from the meter includes the extra 10, which is not going to be decreasing. So you need to minus the 10 from it, and then you can say, yeah, now it's going to decrease in the same sort of way. So this is no longer our standard exponential decay equation. It's a slight variation on our standard exponential decay equation. Not a big variation, slight variation. A poker has one end in the fire, so you can see that end in the fire. And the temperature along the poker, so as you go away from the end that's in the fire, this bit, if you touched it here with your hand, you would probably have melted your skin and left it behind by the time you removed your hand. But if you touched it here, maybe you'd just scald your hand a little bit. And if you touched it here, maybe it'd be absolutely fine. It might feel hot, but it won't harm you. So the temperature is going to decrease as you go away from the bit that's in the fire. I don't think that's news to you. I think you kind of knew that that was the case, even though you've never seen an open fire and used a poker before, because they banned them by the time you lot were born. Have you seen a fire? Have you had a bonfire in your garden? Yeah. Oh, you have. Who did it? Okay, and did you do some jacket potatoes on it? Did you cook anything on it? Okay, and what's the bonfire for then? Did he have some stuff that he needed to burn? Okay. So was it an open bonfire, or was it in like an incinerator? Was it in a special?
It was an old barbecue that we had. We just put it inside the old barbecue.
Okay. So did you use the barbecue then? Or you haven't used that before?
No, we
For barbecuing food?
No.
Okay. All right. Do any of you know what a Decay is? Or I don't know if it's called a Decay or Sugri or what. My sister's got one. She goes on and on about it, and she cooks stuff on it. It's how they used to cook. It's how they used to cook in India. So in India, they used to cook on that metal thing, and you put all the coals or wood or whatever in there, and you put all these shelves, and you cook it. And the top shelf, the fire is in the bottom one. No, I don't think the fire is in the top one, and then the one below that is quite warm. By the time you get to the bottom one, it's not very warm at all. So when I was in school, in my geography class, my teacher told me, he said, in India, they get cow pats, which is cow poo, and they put it on the wall to dry. And then once it's dried, they use that to cook with. So, so I was like, and we were all like, yeah, that's disgusting. And then I went home and I told my mum, I said, Mum, in India, this is what they do. And she goes, yeah, that's how I used to cook. And I was just totally grossed out. And I go, oh, Mum, that's disgusting. And I refused to eat anything she made from then on. I said, I'm not eating anything you've made at all because you've been touching cow pat. I don't want to know anymore. And you think that cooking with cow pat is all right, and I don't want to know anymore. I was like, I don't know what I'm going to. I lasted about 3 days, which was quite good. You imagine 3 days of just eating biscuits. Yeah. So I couldn't cook anything. I was like, I don't know, 12 or 13 at the time. So, and then eventually I thought, oh, I'm so hungry, I'll just have to eat what she makes, even though she's got cow pat hands. And then since then, Mena's dad says, I was telling Mena's dad about this, and he said to me, yeah, but have you ever tasted the food that's cooked on using cow pat fuel? It tastes lovely. So he was going on about chapatis cooked on cow's pats as a fuel. And he said, oh, you'll never taste a chapati like that. It just tastes amazing. So when we were in India, asking everyone, can we have chapatis cooked on cow fats? And I'm guessing they don't do that anymore. So they're all looking at me like, what is wrong with you, you weirdo? And so, funny that. Okay, so, all right, what are you going to define as your variables? Good.
Temperature.
Mhm. Theta equals temperature on poker, and x equals distance from end in fire. That's going to be in degrees C. That's going to be, I don't know, either in centimeters or meters. I'll call it meters. Imagine you've got like a 1 meter long, 2 meter long poker, something like that. And then form the differential equation for that. Sam. Yep. That is not an exponential decay equation. If that was a theta, then it would be an exponential decay equation. That and that need to be the same for it to be an exponential decay equation. No, sorry, hold on. Oh, we don't have our previous ones, do we? We've lost them. Okay, so that's not an exponential decay equation. Our exponential decay equation was generally of this form: minus dm by dt equals kt, km rather, km, so it was like that. And so this and this were the same, m. Rate of change of m was proportional to m. The rate of decrease of m was proportional to m. Lizzie is a parachutist. She knows that the drag on her when free falling is proportional to the square of her velocity. So we've got this equation here, which tells you the drag on her, the force upwards. And it tells you it in terms of things like the density and the drag coefficient and stuff like that. But we're not really going to bother with that equation too much. We're going to just really simplify it a lot for ourselves because that looks too complicated and too much like physics. We're just going to say, we're going to ignore all of that and just say, call all of that K. Just replace all of that with K. K. So the force of drag on her is K times V squared. And that's what they say here. The drag on her when free falling is proportional to the square of her velocity. So that's that statement here. There. Mathematically, that statement is the force on her. So what will happen when she jumps out of the plane? She's not free falling, is she? That's totally wrong, that diagram. It's got a picture of a girl parachuting, but she's under canopy. She's not free falling. She should be just like that with no parachute open behind her at all. I think I just like the look of the parachute, so I just put it on there anyway. So what will happen is when she jumps out of the plane, her weight, her mass times gravity, is going to cause her to accelerate downward. So she's going to accelerate downward. But as she starts to accelerate, there'll be more upwards force, more upwards drag. And so that means she won't accelerate as quickly after a little while. Initially, she'll accelerate fast. And then she won't accelerate as fast. And then at some later point here, much later, she'll almost have stopped accelerating completely. We'll say that she'll have reached terminal velocity. Terminal velocity is you're falling so fast through the air that the force that's pulling you down, your weight, and the force that's acting in the opposite direction, the drag, are balancing each other out. And so therefore you can't accelerate anymore because there's no resultant force on you anymore. The forces are balanced. You won't accelerate anymore. And so you reach terminal velocity. And she said that for her, terminal velocity is about 28 meters per second. She knows because she's done this before, and she knows 28 meters per second is her terminal velocity. Okay. So, all right, we need to form a differential equation. We've got loads of information here. We need to form a differential equation. Matthew. What do you want to define first of all? Variable.
Velocity.
Yep. V equals velocity in meters per second. And time in seconds. Okay, lovely. We've defined our things. Right. Now you've got to form a differential equation. I'll give you a little bit of a clue. Let's. Here's my car. Here's my car. My engine is pushing forward with a force of 1,000 newtons. But the problem is my car's a bit rusty and there's a lot of friction. I'm not even moving yet, so we don't have to worry about air resistance. There's about, I don't know, 400 newtons of resistance in my car. It's rusty. And it's got a mass of, I don't know, it's a crappy car. It's quite lightweight. It's got a mass of, I don't know, 500 kilograms. It's a 6 and 2 CV. Would you know how to work out the acceleration of my car at this particular moment? Go on then.
That's 1,000 minus 400 is equal to 400.
Yeah, positive forces minus negative force equals ma. Define your positive direction. We're going to have, this is our positive direction. We're going to have, this is our positive direction. Nice big arrow when you're showing what your positive direction is. This is my positive direction. My positive force is this one here, which is 1,000, minus my negative force here, it's 400, equals my mass is 500, and my acceleration is a. So 600 over 500 is 6 over 5, which is 1.2, which is my acceleration. Yep, we know how to work out acceleration. Define which way is positive. Positive force minus negative force equals ma. Back to here. Back to you. Which way do you want to be positive? Yeah, she's going down. You're going down. Okay, do positive force minus negative force equals ma.
mg minus k squared.
You don't need mg, you just need m, and then you need a. And if you write a, you won't have a differential equation. Lovely. There's our differential equation. So we've formed a differential equation for that situation. Actually, we haven't done that well in forming our differential equation because we should have also told them what k is, because we know what k is. Even if we pretend we don't know what k is, people won't believe us. They'll say, you know what k is. I know you know what k is. And we'll say, no, honestly, I don't know what k is. And they'll say, yeah, you know what k is. You know that she's got a mass of 125 kilograms, and you know that her terminal velocity is 28. So that would mean that you would know what k is. Am I right there? What is the definition of terminal velocity? What happens to the forces at terminal velocity? Mg equals kv squared. mg equals kv squared. And do you know what her mass is? And do you know what the terminal velocity for her is? So could you work out what k is? Do it.
125 here. No, 620.
And then decimal it.
0.22.
Just do it on the calculator and put in the g as well. Lovely. So we get mg minus 1.96 v squared equals mdv by dt. And so there's our answer. There's our differential equation. Actually, I haven't put in her mass either, have I? I should put in her mass. We know her mass is 125. 125. I'm putting the 125 in there. 125 in there. Okay. Bombarding sodium-23, which is stable, with neutrons. So this is my sodium-23. I've got loads of it. And I'm now going to bombard it with neutrons. So I'm going to fire neutrons at it. And I'm going to keep firing neutrons at it constantly. And as I fire neutrons at it, what's going to happen is some of them are going to absorb the neutron and going to turn into sodium-24. Oh, there was one that turned into sodium-24. Oh, and there's another one that turned into, and there's another one, and there's another one, and there's another one. Some of them are going to turn into sodium-24. So we're going to get some sodium-24 start to appear. But then, in fact, they tell us that the rate at which the sodium-24 appears is constant. So the rate at which the sodium-24 appears is constant. So let's say N1 equals number of sodium-23 that become sodium-24. And T equals time. So dN1 by dt is just a constant. It's just a constant. I won't even use K, I'll use C. Use C. dN1 by dt is C. I won't even use C. C I use when I'm integrating, don't I? I use R. Use R. So the rate at which sodium-23 appear is constant. You get this, you know, I don't know, maybe every minute you'll get 4, maybe. Sometimes 5, maybe sometimes 3, but on average 4 a minute. But then the problem is these sodium-24s are unstable. And so what happens with the sodium-24s is they can decay. They can decay. And they decay much like this decayed. Where's the one that decayed? This one, no, not that one. This one, this radium that decayed. It was dN by dt equals minus Kn. It was minus dN by dt equals Kn, but same thing. So some of these are going to decay. So N2 equals number of sodium-24 that are left after some decay. So dN2 by dt is equal to minus K N2. That's just the same equation as we had a second ago for the radium thing. What am I doing? I don't know what I'm doing. Okay, this is the rate of production of sodium-24 is constant. The rate of decay of sodium is proportional to that of sodium-24. I don't want this N1 and this N2. I just want to know how much sodium-24 there is. Just tell me how much sodium-24 there is. N equals number of sodium-24. T equals time. dN by dt. Tell me that one, please.
I don't know.
Sana. So do you remember before we said that some of them were appearing and the rate at which they're appearing was dN1 by dt, and that was just R. And then we said, yeah, but once they appear, some of them are going to start to disappear. And we said dN2 by dt was minus K times N2 or N, I don't know what we're doing. So what if you combine the two together? What if you get, yeah, but some are being formed, but then some of them are decaying. So what will we get for our differential equation if we're combining the two? Try right here.
dN by dt times 1 minus.
Because I sort of did a lot of the working already. I pretended I didn't, and I pretended to rub it out. But N1 is the number of sodium-24s that have appeared. So the rate at which they're appearing is R. And then the rate at which they're disappearing is minus Kn. I know I called it N1 and N2, but they're really the same thing. They're sodium-24s. So the rate at which they're appearing is R, and the rate at which they're disappearing is minus Kn. So it should be quite easy to just put that together and work out what dN by dt is. R minus Kn. These are the ones that are appearing, and these are the ones that are decaying. Okay, so what you see is there's loads of different situations. Somebody just has to give us some idea of what physics that situation involves, or what technical information we need for that situation, in order for us to then start write a differential equation. So now we're ready to start modeling. So what we do first of all is we form our differential equation, and we've already said you define the variables. We already said that, you define the variables. First thing you do is define the variables. Now, the next thing you do is, now the questions will have numbers in them. So the next thing you do is you pair up the values that you're given in the question. Write down what numerical information have they given you. Just write it all down. In particular, if one of the values is a value of dy by dx, then you need to be careful to get the sign correct. You need to be careful to get the sign correct. If one of the values they give you is a dy by dx or dn by dt or something like that. Then form your differentiation. We've just done 100 of them. Then put in the given values. If one of the given values is a value of dy by dx, then you put it in now before you solve your differential equation. If you're given a value of a rate, then you put it in before you solve the differential equation. Okay, once you've done that, you separate your variables and you integrate it, and then it says you don't always have to rearrange it, but most of the time we probably will rearrange it, but sometimes later on we won't rearrange it. And then finding our particular integral, what we're going to do is put in any other known values in there and then get rid of all the constants. So at the end, we have an equation connecting the two variables with no unknowns in there. Now I say that, but there are some questions where we will always have an unknown. It will be usually in the form of n naught or m naught. And that means that we're working everything out, not knowing the starting amount of whatever that thing was. So the starting amount is called n naught. So if you've got some bacteria in a dish, you don't know how many there are to start off with, you'd say, well, there's n naught. N naught just means the starting amount when you start looking at it. And if you don't know what that is, it's going to stay in all your answers. It's going to be there, well, in all your working, not necessarily in all your answers. Okay, so we're coming back to the first question, and now we've got some numbers to put in. So on your sheet, these numbers weren't in there. So it's the same situation. The boy has got a bowel infection and some stuff is going on. But now we're told some numbers. We're told a test done when he arrived at the hospital showed that he had 1,500 million. Shall we call that time 0? Shall we start our stopwatch when he arrived at the hospital? Yeah. There's no point in starting it 3 weeks ago because we don't know what happened 3 weeks ago. We'll start it the moment he arrived at the hospital. So we're going to say t equals 0, n equals 1,500. Remember, we'd already defined t is time in hours, and n is the number of bacteria in millions. So t is 0, n was 1,500. And then let's say, oh, but yeah, 20 hours later, so a test taken 20 hours later showed that this had increased to 3,000 million. So, t equals 20, n equals 3,000. Okay. So these are the bits of information we've got. We've got this bit of information here, and we've got that bit of information. Those are the 2 bits of numerical information. Now we've got the differential equation, which we know because we did it already. Doctor says the rate of increase of bacterial population, that's dn by dt, is proportional to equals k, the number that are present there, n. And now we've got the crunch point. It says here, if the number reaches 5,000 million, then it's dire straits. He's going to have to, they're going to have to remove his bowel and give him a colostomy bag. So this is what we want to find. N equals 5,000 million. What would t be? We need to find that. How long have we got before we have to start operating on it? Okay, right. So looking at these numbers, there is no value of dn by dt. There's no value of dn by dt. So nothing here can be substituted in here yet. So let's not worry about that. Normally, if there's a dn by dt, we'll substitute it in now. If there isn't, forget it. Don't worry about it. Okay, what next? We can solve our differential equation. We can separate the variables. So 1 over n dn equals k dt. Separate the variables and then integrate both sides. So let's put a big integral sign in front of each side. So big integral sign here, big integral sign there. And then now we're ready to integrate it. So that gives us ln n equals, we're integrating k with respect to t. So that's going to give us k times t, kt. We need a constant. Let's put an a in here. Let's put a constant a in there. And then we could make n the subject of that. Get rid of the ln, e to the power of both sides. That's going to give us an equals e to the kt, and then divide by a, and then that's going to give us n equals 1 over a. I'm just going to rename the 1 over a b. We talked about that already. If you don't know the number, calling it 1 over a or calling it b doesn't make any difference. You don't know what it is in either case. N equals b e to the kt. Okay, So this is our equation, but it's got some numbers that we need to find out. We need to know what B is, and we need to know what K is. We need to figure those out to complete the equation. So now we'll start putting in the information they gave us. Let's start off with this bit of information. T is 0, N is 1500. T equals 0, N equals 1500. Let's stick that in. 1500 equals B, E to the 0. Well, E to the 0 is 1. So that just immediately tells us that B is 1500. So B is 1500. So we can replace that B. So now we get N equals 1500 E to the KT. You will always find that's the case for the exponential growth equation and the exponential decay equation. Do the same for both. If they tell you the starting amount, that is just what will go here in front of the E to the power. So that number in front is always the starting amount, the amount that you start off with. N0, we might call it. If they tell you what N0 is, it just goes there in front of the E. What else do they tell us? They tell us when T is 20, N is 3000. So the next thing they tell us is T equals 20, N equals 3000. So we'll put that in to the equation. So that gives us 3000 equals 1500 E to the 20K. Let's divide both sides, so 1500. 2 equals E to the 20K. Let's ln both sides. Ln 2 equals 20K. Let's divide both sides by 20K equals ln 2 over 20. So there's my constant, ln 2 over 20. There's my unknown constant, is ln 2 over 20. You can decimal that. Can you stick that in the calculator for me? But if you do decide to decimal it, because this number goes in the power here, you have to be accurate with it. You have to go like to quite a lot of decimal places, like 6 or so decimal places. Because this number goes in here, because K is in the power, a slight difference in K will make a big difference in your answer. So that's why if you do decimal it, you have to go quite accurate with it. Tell me what it is, Sam. Okay. You're just going to say 0.03. But he said be quite accurate with it. That's quite accurate, isn't it? Okay. So you keep the exact number, yeah? Or even better, just leave it as ln 2 over 20. And I will just use this rough approximation. I'll just use it. Oh, I can't be bothered to do it more accurately than that, yeah? Okay, so, which is wrong, of course. And so now we know what K is. My equation is N equals 1500 E to the 0.03 T. Obviously, that's not very accurate, and it should have been more accurate. Obviously, you've done it more accurate than that. Or better still, you've used ln 2 over 20 and just left it as ln 2 over 20. That's far more accurate. Okay, so what do we need to do now? We need to find out when will the number of bacteria reach 5,000, because that's when it's crunch time for him. So N equals 5,000, T equals question mark. 5,000 equals 1500 E to the 0.03 T. And so that gives us 50 over 15, so 10 over 3 equals E to 0.03 T. And then ln both sides, ln of 10 over 3 and divide by 0.03 equals T. You work out yours will be more accurate than mine. I'll work out mine. Mine will be terrible and I'll be embarrassed by my answer. So we get ln 10 over 3 close bracket divided by 0.03. So I got 40. Just try it and learn 10 over 3 close bracket divided by. I got 40. I got 40.13. I got T is 40.13. So I think we've got 40 hours left to save him. You did it more accurately. What did you get, Matthew?
I got 34.7.
34.7. Do you all get that? 34.7? 34.7. Look how massively out mine was. That number needs to be 6, 7, 8 decimal places, or better still, 6 significant figures. And then it will be acceptable. So what did you get again? 37.4.
34.7.
Is 34.7. Okay. So we've done the question. It says, boy suffering from bowel infection. When he arrived at the hospital, he had 1,500 million. Test taken 20 hours later showed it increased to 3,000 million. If the number reaches 5,000 million, they'll have to remove his bowel and find a new treatment, and he'll have no bowel left. So it's all right, don't worry. We've got 34 hours, which is more than a day left. So I'll do it tomorrow. I'll figure out how to solve it tomorrow. I'm going to go home today, and tomorrow I'll come back and figure out this problem. It won't be that hard. Just finding the right antibiotic should do the trick. Actually, you're looking rather concerned about the poor boy and the really bad doctor who thinks he's got 34.7 hours left to save him, but he doesn't. When did we start the clock? And is that now when we're doing the question, when he came in? Because we know that a test was done 20 hours after he came in. So we know that 20 hours has already passed. At best, we've got 14 hours left to save him. If I go home, by the time I come tomorrow, it'd be too late, and he's going to have like his whole bowel removed and stuff like that. So that would be terrible. It would be a terrible mistake. The answer is we've got 14 hours left, 14.7 hours left. Okay. Next question. In the Amazon rainforest, the canopy height is 8 meters. So that was, we talked about this before. We said this is the canopy where the tops of the trees are. And we know that that's about 8 meters. So that's about 8 meters on the ground. And it says plants at the top. So if you have a plant here at the top, then that's going to receive 5 lumens of light. 5 lumens of light. Because the sun reaches those plants at the top quite happily. So here's the sun. You get loads of sun here if you're at the top of the canopy. By the time you get further down, you're getting a lot less sun. Okay, so him at the top gets 5 lumens of light. If you're 4 meters below, so if you're a plant that's growing here, and you're 4 meters below the tops of the trees, then you're only going to get 3 lumens of light. 3 lumens. The jewel orchid needs 2.2 lumens. So the jewel orchid needs 2.2 lumens. Let's draw that in a nice jewel orchid kind of color. Oh, that looks the same as the color we've got for the other one. There's the jewel orchid, and it needs 2.2 lumens of light. 2.2 lumens of light. Okay. We've already started this question before. We defined L as the light level, which is in lumens, and we defined X as the depth below the tops of the trees. meters. And we said dl by dt decreases negative in proportion to the square root of x. Did I get that right? The amount of light decreases, so minus dl by dt, in proportion to the square root of the distance below the tree canopy. Did I get that right? Asking that to Sam.
Isn't it's the distance?
Yeah. Yep, depth, depth below the. If you talk about, like, if you're measuring from the top down, you often refer it as a depth, don't you? So you don't say what is the distance of the bottom of the swimming pool. You say what is the depth of the water or something like that. You can call it distance. You can call it depth. That doesn't matter. Is my equation okay then? Yes, it's nothing to do with time, this question. It's not to do with dusk. It's nothing to do with, oh, look, it's dusk and the light level is dropping. Oh, how is the plant going to survive? They survive nighttime. They don't have to do that. So, okay, so it's dl by dt. Okay. Right, let's separate the variables. Minus dl equals kx to the half dx. Integrate both sides, put a nice big integral sign in front of each side, and then integrate it. So, oops, how did that come out? Try that. So let's integrate it. So that gives us minus L equals K x to the 3/2 times 2/3 plus C. Okay. You know this K, I don't know what K is. At the moment, I don't know what K is. I don't know what K is. So if you say no, but you've got to multiply it by 2/3, when you multiply it by 2/3, you're still going to make a number that I don't know, because I don't know what K is. So I'm going to replace this K times 2/3. I'm going to say, well, I don't know what K is. If you multiply it by 2/3, I'm just going to call it A. I'm just going to call it A. Okay. Right. Let's put in some numbers. They tell us that a plant at the top receives 5 lumens. So if x is 0, L is going to be 5. So x equals 0, L equals 5. So minus 5 equals A, 0 plus C. Okay, so C must be minus 5. The C must be minus 5. I can get rid of the C and change it to minus 5. In which case, I might as well tidy up the equation by multiplying through by minus 1. So L equals 5 minus A x to the 3/2. Multiply through by minus 1 just to tidy up. Now, the other thing I know is I know when L is 3, x is 4. So that's this one. X equals 4, L equals 3. So 3 equals 5 minus A, 4 to the power 3/2, 4 to the power 3/2. So that's going to give me 8A. And so that's going to give me 8A equals 2, A equals 1/4. So now I know that A is 1/4. I can replace the A here with 1/4. So replace that A with 1/4. Now my equation is fully formed. The only unknowns are the variables, L and X, which are supposed to be variables. So you're not supposed to know those values until you want to find it. Now, finally, I can do the 2.2 lumens, which is my joule awkward. So put in L is 2.2. put in L is 2.2 and work out, put in L is 2.2 and then work out what X is. Put in L is 2.2 and then work out what X is. Tell me what height the jewel orchid needs to grow at in order to get the right level of light. You know, they're adapted for their individual light levels and their requirements. So if you put the jewel orchid at the top, it would be too bright for it. It wouldn't survive if it got too much light. The ones at the top are ones that are adapted to being at the top and can cope with that level of light. Because, you know, being at the top has its own problems. How do you get there for a start? You put in L is 2.2. What value of X did that give you? You put in L is 2.2. What value of X did that give you? Sam? Oh. Just put in L is 2.2. Minus 5 from it. Divided by minus a quarter. And do the 1.5 root. Do the, you know your root button, you've got a root button like this, root, box, box. Put in 3/2 in there and put in the answer in there. 5. X is 5. So it's got to live 5 meters below. 5 meters below. You know that's actually true. I actually looked all of that up. What height does a jewel orchid live? What light level does it need? I looked it up. And that's actually true. You can check it out. I don't just make up any old random questions. I looked them up, and apart from the bread one with the yeast, where I just couldn't bother to look it up. Okay, you do this one. You do this one. So you've got to start by defining the variables, but we've already done that. You don't know the units of it. I'm going to do time in hours because it says 30 minutes. That's half an hour. So you might as well start talking about hours now. The initial number of yeast cells is N0. So that's telling you P is 0, N equals N0. And it takes 30 minutes to double. That's telling you T is a half, N equals 2N0. Those are the 2 bits of information they're giving you. This doesn't even count as a bit of information, does it? Really? At T is 0, the initial amount is, well, the initial amount. We're not telling you how much. It doesn't really count, does it? Anyway, never mind. You just have to make do. Give me your final answer exactly and approximately. Give me your answer exactly and as a decimal. I want both, exact and as a decimal. Exact is nice because it's accurate, but decimal is nice because it gives you an idea of exactly how long we're talking about. equals see here. Are you putting in numbers in here?
4 times.
I would carry on and make n the subject first. So I divide by a, make n the subject first, because then you'll find it easier later on. Okay. Yeah, I would have made, yeah, you did make n subject, and then so when they tell you t is naught, n is n naught, what you're doing is you're putting in n is n naught. So that's going to be n naught. Okay? Not naught, n naught. Because if you start off with no yeast, you're not going to make a good bread here. You're going to make chapatis. Yes. Yes. You don't need to take the k. You can just leave the k there. Just take the n there. So leave the k there. It's easier. Otherwise it becomes awkward. Okay. Carry on from there. Don't forget the constant, ln AF. So you all did the correct thing. You separated the variables. You said 1 over n dn equals k dt. And then you integrated both sides and it gave you ln an equals kt. And then you rearranged it to give you n equals d e to the k, d e to the kt. That's the exponential growth equation. That's the exponential growth equation. It looks like this. It looks like this. It's the exponential growth equation. It's the e to the x graph. It's the e to the x graph. And then you've got a squash of k along the x-axis. So I'll squash it by k along the x-axis. And then you've got a times b along the y-axis. So I stretch it by b along the y-axis. And what you get when you stretch it by b along the y-axis is instead of having an intercept of 1, it has an intercept of b. And so that's what the graph looks like. It looks like this. It's an exponential growth graph. And it starts from b. B is whatever the original amount is. So b will be whatever the initial amount is. But they tell us the initial amount is n naught. So that's just going to be n naught. So n equals n naught e to the kt. Then, after that, the next piece of information they tell us is when t is a half, n is 2n naught. So we'll put that in. T equals a half, n equals 2n naught. 2n naught equals n naught e to the k times a half. T is a half. Divide both sides by n naught. And then ln both sides. Ln 2 equals a half k. And then k equals 2 ln 2. So I now know that k is 2 ln 2. I can replace the k in here with 2 ln 2. With 2 ln 2. I can replace that k with 2 ln 2. And so this is my equation. And that's it. That's as good as that equation is ever going to get, because I'm never going to know n naught in this question. And then they ask me, yeah, but how long does it take to treble? So they want to know when n equals 3n naught, what is t? So I'm just going to put in 3n naught into here. I'm going to put in n is 3n naught. So I'm going to put in n is 3n naught equals n naught e to the 2 ln 2 2. And then I'm going to divide by n naught again. And so that's going to give me 3 equals e to the 2 ln 2t. And I'm going to ln both sides. So ln 3 equals 2 ln 2t. And then I'm going to divide by 2 ln 2. Ln 3 over 2 ln 2 is t. So that's the answer for t. Then when you decimal that, what does it give you? If you decimal that, right here, what did it give? 0.792. So 0.792 hours. And what is 0.792 of an hour? Well, it's a bit more than 3/4 of an hour. It's a bit more than 45 minutes. What does it turn out to be in minutes? 47.5 minutes. So if you want your dough to treble, or the amount of yeast in your dough to treble, then you've already left it for 30 minutes and it's doubled, but it's only going to take another, well, 17 and a bit minutes for it to treble. Not going to take as long to treble as it did to double. A large tree stump is rotting. Its mass decreases at a rate proportional to the amount of stump left. Initially, its mass was 20 kilograms and it was decreasing at 50 kilograms per year. We've already done this. We said m equals mass in kilograms, and we said t equals time, and we can see that it's in years because they use the word year in the question. And we said that minus dm by dt is equal to km. And we said that that equation is the exponential decay differential equation. And then we look at the information they've given us. They tell us when the mass initially means t is 0. So t equals 0, its mass was 200. So t equals 0, its mass was 200. And it was decreasing at a rate of 50. So t is 0, m is 200, but also dm by dt is 50. So that's quite a bit of information to tell us. They've told us everything we need to know at t equals 0. At t equals 0, the mass is 200 and dm by dt is 50. Hold on, did I get that right? It says it was decreasing. Its mass was decreasing at a rate of 50 kilograms per year. And I said dm by dt is 50. Did I get that right? Good? Yes, yeah, of course it is, minus dm by dt. It says here, be careful to get the sign right. So I've got to be careful to get the sign right. You'll kind of know if you've got it wrong, because the k will end up being negative, and the k kind of should be positive. Unless it's a question where you've not followed the rules, the k should be positive. Okay, so, and it says, how long will it take for the mass to halve? So m equals 100, t equals question mark is what they want us to find. Okay, this time we do have a rate. So when we have a rate, we put that into the differential equation before we've solved it. So minus dm by dt is 50 equals k, and that's when m is 200 equals k 200. So k is a quarter. That was quick and easy. I already found k. In a second. That was nice and quick and easy because they told me the value of the rate. Okay, so we've done that. Now you carry on and you do the rest of it. Solve your differential equation. Separate the variables. Solve the differential equation. And then tell me how long I'm going to have to wait. I need the mass to go down. I want to plant some stuff where that stump is. I tried to work it out myself, but I was stumped. Divide both sides by m. Put dt on the other side, integrate both sides. Put in the constant when you've done the integration. Might as well make m the subject. Once you've made m the subject, there's a bit more information you need to sling into your equation. You need to sling this in. Here's not m is 200. You need to sling that into the equation. That will give you the constant, the unknown constant. You might have called it b by now. It will give you that unknown constant. When we write the 1 over a, we just replace it with b every time, so then we don't have to have that 1 over a in there. It's too awkward the way of doing it. Just, you know, when you divide by a, we replace that 1 over a with b. Yeah. Yeah. Yeah, perfect. Why is it under? Really on the line there. Divide by the a and replace the 1 over a with b. Minus 1. So Viren, after I've integrated it, what you'll see me first of all do is you'll see me first of all take the minus over to the other side. Then I'll get rid of the ln, so I get am equals e to the minus 1/4 t. Then I will divide by a, m equals 1 over a e to the minus 1/4 t. And then I will replace this 1 over a with b. You've seen me do it 100 times now. Replace that 1 over a with b, because I don't know what it is. No point in calling it 1 over a. Might as well just call it b. Now you're putting in t is 0, m is 200. b is 200. Didn't I tell you that this number here in front of the e on an exponential decay equation or an exponential growth equation, that number b will always be the initial amount, which is 200 in this case. It turns out it's 200, but we knew it was going to be 200. We didn't need to do that calculation. We knew it was going to be 200. This comes up so often that you'll end up wanting to speed it up a bit. There's our equation, and now we just need to find when m is 100. 100 equals 200 e to the minus 1 t. Divide both sides by 200, a half equals e to the minus 1/4 t. Ln both sides, minus ln 2 equals minus 1/4 t. And then times both sides by minus 4. T equals 4 ln 2. That's the exact time. If you decimal that, what does it come out as, Sana? 2.77 what? 2.77 years. It's going to take almost 3 years for half of the sum. Actually, there's a much quicker way of working this out. We did it the long way. I'll show you the quick way of doing it. It's much quicker though. You'll be annoyed at me for having made you do it the slow way when I show you the quick way. The quick way, you don't need to know differential equations to do it the quick way. You can just be like this be like a layperson. This is how they would do it. Somebody who doesn't want to study maths at all. Initially, its mass was 200 kilograms. Okay, 200 kilograms, it's a lot, but it's all right. It's a tree. They're quite heavy things. The stump of the tree is quite heavy. And decreasing at a rate of 50 kilograms per year. Okay, so in 1 year, 50 kilograms of it are gone. It'll be at 150 kilograms. And in another year, another 50 kilograms would have gone. It'll be at 100 kilograms. So for the mass to halve, take 2 years. Easy. You can't argue with that sort of simple logic, can you? There'd be nowhere not to agree with me. Yeah, you kind of can tell by my demeanour. Don't agree with him now because he's talking rubbish and he's purposely talking rubbish. Do you like my quick method, Matthew? It's decreasing at 50 kilograms per year. Starts off at 200 kilograms. How much is going to be a year later? 50 kilograms less. It's 150. How much is going to be another year later? 100. 2 years is how long it will take. You in your 2.77 years, you don't know maths. Right there. Do you like my method? What is faulty about my method?
So after a year, there'll only be 150 left. So they'll be proportionate to 150.
So what Rajvi is saying is, look, that 50 kilograms a year works on day 0. That's the rate at which it's losing. But within a week, that's dropped from 50 kilograms a year to 48 kilograms a year or 49 kilograms a year. And within another week, it's dropped again. And by the end of the year, it's dropped quite a bit. It's no longer 50 kilograms per year. It's quite a lot less. So even at the end of 1 year, it won't have dropped by 50 kilograms. That's the initial rate at which it's losing mass, but it's not losing 50 kilograms. It's losing 50 kilograms per year. But if you work that out as a day, it's 1 over 365 times 50 kilograms. So roughly a seventh of a kilogram it have lost. And then immediately that rate will have slightly gone less and then slightly gone less. The rate is changing all the time. It's not staying at 50. If it was staying at 50, when its mass was 40, when it has really rotten down a lot and its mass was 40, it's going to have to lose 50 kilograms that next year. How's something that weighs 40 kilograms going to lose 50 kilograms? That's impossible to do. So, so you can't do it by assuming this is not a constant. This is not a constant. It's varying minute by minute. It is varying minute by minute, but I mean, you won't notice it varying minute by minute, but you will notice it varying year by year. At the end of the first year, it'll be a lot less than 50 kilograms per year. Okay. Radium is a nasty radioactive substance that decays over time, but don't worry, if you need to get rid of some, just hide it under your bed. It will decay and eventually there'll be none left. A sample will lose mass at a rate proportional to the mass remaining. Radium has a half-life of 1/6. Okay, I don't know what these words mean. I haven't studied physics. I don't know what these words mean. These sound like physics words to me. Can you translate that into English for me so that I know what this is talking about? Radium has a half-life of 1600 years. What on earth do those words mean? Good. Oh, hold on. Who doesn't study physics? Oh, okay. Oh, right. There's a lot of people not studying physics. What's wrong with you, though? Good. What does it mean when somebody says radium has a half-life of 1600 years? It's not self-explanatory. Not
Like half its value is 1,600 years. So it would only last.
No, I get what you're saying, and it's a reasonable interpretation of what it says, but that's not what it means. Sam. Matthew.
Does it mean that like half of its decay is it reaches its half of its maximum decay by?
You start off quite well, but then it kind of got a bit confused. It's sort of right, but it's a bit too complicated and confused for me to make sense of. Yeah. we're going to have to get a physicist to tell us, tell us in simple English what this means, not in Matthew's, well, it has a maximum rate of decay, but in 160 years, it will have reached half of its maximum rate of decay, which is actually correct.
The time taken for the amount of radioactive substances.
Yeah, so in 1600 years, its mass will have don't you need to know that, like even just to get past GCSEs? I think you need to know that just to get past GCSE. How did you not? And science is obligatory at GCSE. You can't not do science, can you? You have to do science, you have to do maths, you have to do English. How did you not survive that long without knowing what the definition of half-life is? Okay.
So we didn't do our GCSEs, so.
Oh, of course, you didn't have to do GCSEs. So you don't know nothing. Basically, you can't even walk down the road without falling over. Wow. Okay. Well, could you imagine in like 20 years' time when you lot are like the, you know, leading businesses and, you know, sorting out, oh, it's going to be such a mess. Okay. Fine. Oh, I've got an apostrophe there. I didn't have one. Okay, you do the calculation. You do the calculation. What percentage of the mass remains after 100 years? We've already done some of this question. We already did the bit where we define the variables. You should recognize that as the exponential decay equation, so you know exactly what's going to happen next. You're going to divide both sides by m, you're going to take the d here, the other side, you're going to integrate both sides. I'm going to cheat. I'm going to go straight to what I know the answer is. In this question, you're never going to know what M naught is. You're never going to know what M naught is. They're never going to tell you what M naught is. You're never going to know what M naught is. But you do need to figure out what K is. You do need to figure out what K is. And you use this piece of information to figure out what K is. When you put in t as 100 in there, the answer will be in terms of m naught. That's fine. We were expecting the answer to be in terms of m naught. We weren't expecting anything else. We were expecting the answer to be in terms of m naught. An answer to the question?
On the board, how you get it, m equals m average. I didn't think, is that the same? That was to
So the first thing you need to do is put in t is naught, m is m naught. You don't need to put that in first. You need to put in t is naught, m is m naught. The initial mass is m naught. Look at the question. It says the initial mass is m naught. Initial means t is naught. The initial mass is m naught. You need to put that in first. T is naught, the mass is m naught. I did that, but I did it so quickly I didn't even show it on the board. You can just leave it as, ln a half is the same as minus ln 2.
Yeah.
So really I had ln a half, but then I just wrote it as minus ln 2. Yeah. Just finish it off, give me the answer. Yeah, stick it in the calculator. Obviously you can't put the m naught in the calculator, but you can sit the rest of it in the calculator. What did you get? So you worked out the t with m naught, and so that's how I ended up with that equation. This will always be the case, Stuart. This number here will always be the initial amount, the number in front of it. We always get b, but b has to be the initial amount, whatever the initial amount. So if the initial amount is m naught, that's going to be m naught. If the initial amount is 100, that's going to be 100. So our answer was, we're putting in t as 100 instead, so m equals m naught times e to the minus ln 2 over 1600 times 100. So those noughts will cancel out. So all you've got to do is type in this bit into your calculator. This bit into your calculator, which is the minus ln 2 over 16. E to the minus ln 2 over 16. And that will give you m equals m naught times, what does that give you when you stick it in the calculator, Dana?
0.957.
Any more decimal places? Okay. Are you sure it was 0.957 then?
6.
Okay, so 958 then. That gives us m equals 0.958 m naught. So after 100 years, the mass is 95.8 or 0.958 of m naught. In other words, it's 95.8% of m naught. In other words, only 4.2% has gone. So if you stash it underneath your bed, in 100 years, which will not be your lifespan if you stash radium underneath your bed, your lifespan will be severely curtailed. But in 100 years, there, 4.8% of it will have decayed. The rest of it, 95.2%, will still be there. Oh, was it 95.2? 95.8%. 95.8% will still be there, and 4.2% will have gone. Okay. Newton didn't just come up with the 3 laws of cooling. He discovered the law, the 3 laws of motion. He discovered the law of heating and cooling. We talked about this. This was the Coke thing. And it was theta equals temperature of Coke and T equals time. Well, it's going to be in hours because I can see from these units that that's going to be in hours. And that's going to be degrees C. And we said minus d theta by dt, minus d theta by dt was equal to K. And then what was room temperature? 20 minus theta. That was our differential equation that we formed. Now, what information have they given us here? They've said, right, initially means T is 0. T equals 0. The Coke is at 5 degrees C. Theta is 5 degrees C. And its temperature is increasing, and d theta by dt, oh, hold on, I've written minus d theta by dt. I shouldn't have written minus d theta by dt, I should have written d theta by dt. Its temperature is increasing at a rate of 30 degrees C per hour. D theta by dt is 30 degrees C per hour. So this is the information that they're giving us to put into this equation. So one of the things you notice immediately is this information here, these 2 bits out of that information, the d theta by dt and theta is 5, those can go into here and into here. And so you can find K straight away. You can put those bits of information in even before you solve the differential equation. You can put those in. If they give you a value of the rate, you can put that in even before you solve the differential equation. And then once we found out what K is, we can then separate our variables, solve our differential equation, and then put in the rest of the information, find the unknown constant, integration constant, and then once we've got our equation, we could say how long it takes to reach 18 degrees C. Once you found out what K is, you can separate your variables. And put a big integral sign at the front. Then you can integrate both sides. You get a constant of integration. No need to.
But if you do it, it's all.
Yeah, it's fine. It's fine. Then we're going to integrate both sides. We'll get an A inside the ln. Then we'll rearrange it. Make theta the subject. And then we'll put in T is 0, theta is 5. That will tell us what temperature it was. That will tell us what temperature it was. That will tell us what the constant was. And then once we know what the constant was, we've got our equation, and then we can just say, okay, how long does it take to reach 18 degrees C? We can just put in theta is 18 and work out what T is. "18 degrees C will be practically undrinkable for Coke." Where did you find the big?
It's a bit different because I didn't get a room.
You'd still get a lid.
So, how would I go?
How did you open up those brackets?
So I worked out K's
Yeah.
and 2, so it'd be 10 minus 2.
Yeah.
Oh, 15.
And you put 10 at the front, which isn't right.
Then really just.
No, hold on, that's still wrong. Yeah, look at yours.
That would be 10 minus
2 times 20 is not 10.
2. Oh, that's 10.
You're multiplying now.
It's 10. No.
Now you need to collect the. Hold on, I don't know what you've done. Between here and here, what have you done? Have you multiplied by something? Have you divided by something?
Divided by minus 2.
No, that doesn't make sense. You divide by minus 2 theta. You don't divide by minus 2 theta on that side. You divide by minus 2 theta, yeah? You can't say divide by minus 2 theta on that side. That's not correct.
I can divide by that.
So you just divide by minus 2 theta, yeah? Divide 3 by minus 2 theta. That's how we say it. So if you divide by minus 2 theta, you're going to minus 1 over 2 theta d theta by dt equals 40 over minus 2 theta plus 1. You have to bracket it first, yeah? Which is why there's no point in multiplying it out, because you're going to have to bracket it before you can move it down, anyway. What's the differential of ln 20 minus theta?
1 over 20 minus theta.
Sure it is, Nathan. Whatever you say, Nathan. What's the differential of x? What's the differential of ln x squared minus 3? Because Nathan says it's 1 over x minus 3.
9 times it by 2x. Inside.
So what about your one?
Minus.
Yeah, fantastic. Yeah, perfect. Yeah, that's all right. We need to get rid of B. So before we do that, we need to get rid of B. Now, if you look at the top, they told you 2 bits of information. They told you when t was 0, theta was 5, and they told you t was 0, d theta by dt was 30. Now, we've used this but we haven't used this. So you can put in t is 0, theta is 5 to get that final bit there. Lovely. So we end up with minus ln a 20 minus theta equals 2t. So that gives us, take the minus over to the other side, a 20 minus theta equals e to the minus 2t. Divide both sides by a, 20 minus theta equals b, e to minus 2t. And then make theta the subject, 20 minus b e to minus 2t equals theta. Slam in the extra bit of information. T is 0. Our Coke is at a drinkable 5 degrees C. 20 minus b e to the 0 equals 5. E to the 0 is 1, so b is 15. And so that gives us theta equals 20 minus 15 e to the minus 2t. There's our equation. All we need to do is slam in theta equals 18 and work out what t is. So put in theta is 18, put in theta is 18 equals 20 minus 15 e to minus 2t. 15 e to minus 2t equals 2. 2 over 15 equals e to the minus 2t. Ln both sides, so ln of 2 over 15 equals minus 2t. Divide both sides by minus 2. A half ln 15 over 2 is equal to t. Stick it in the calculator and you get an answer that's quite close to 1. So t equals 1 hour. So it will take an hour for that Coke to become completely undrinkable. Actually, the funny thing about it is these calculations, when you do them, if you do them properly and your starting information is correct, then the predictions they produce are fantastically accurate. They are really good. And there are modifications we can do to improve our model. So at the moment, our model doesn't take into account things like, it considers the room as some sort of a space which has no disturbances, nothing, no air blowing around it. It considers the room as something where its temperature never changes. And of course, if you put a hot object in a cold room, then that will warm up the room as well. And if you put a cold object in a warm room, that will cool down the room. So although the room is warming up the Coke, to a much lesser extent, the Coke is cooling down the room. So the room probably won't stay at exactly 20 degrees C, although a room is a lot bigger than a can of Coke. So therefore, it's not going to change much. The Coke isn't going to have that much effect on it. These predictions are fantastically accurate, even at this simplistic level of modeling. They're fantastically accurate. They work really, really well. So that's why maths or physics, if you like, I don't know which you'd call this, maths or physics, it's sort of a bit of both, isn't it? Works really well when you are making calculations like this, when you're trying to send something into space and you want to see, you know, okay, at what point will you need to adjust its trajectory to bring it into the orbit of whatever it is you're trying to photograph or orbit. Those calculations worked extremely well, you know, to very high levels of precision. Whereas, on the other hand, if you're trying to work out how many cases there are going to be of Omicron, it's really hard to work that stuff out. And the reason is the model works fine if no one knows anything about the fact that they've got Omicron or that there's a disease or anything like that. But once that you tell people, oh, there's this new variant called Omicron, they change their behavior. So all of a sudden, the growth that you were seeing before you told them that Omicron was around, when you just detected it and you hadn't mentioned it to anyone else, suddenly changes when you tell people, because some people say, okay, well, I'm going to behave differently now that I know that there's a new variant around. And other people say, well, I'm not going to behave differently. And you get so much variations and fluctuations that it's almost, you know, the predictions go wildly out because of human behavior. So if you're modeling physical, non-biological systems, this tends to work incredibly well. As soon as you have biological systems, it increases the complexity of your modeling. But as long as it's just like, I don't know, you know, rabbits and foxes and stuff like that, it still works pretty accurately. When you bring humans into it, it increases the variability massively, and it no longer seems to work as well. And that's why people complained about the mathematical modeling of the you know, virus and you know, the number of cases you're expected to get and stuff like that. People complain about that, and the reason is because the things that we do affect it enormously. And so, you know, the things that the politicians tell us to do and what we choose to do affects things enormously. But for these kind of systems, the calculations are phenomenally good. We'll skip this question. Car traveling at 80 miles an hour on the motorway, and the driver notices the brakes aren't working. Being a physicist, he knows if he cuts the engine, then the car will decelerate at a rate proportional to its speed. 2 seconds later, his speedo reads 20 miles an hour. How much longer before his speed drops below 5 miles an hour? Okay, so what have we got? We've got, let's look at the variables that we're going to define. So we're going to have V is his speed or his velocity, which is going to be in miles per hour. And then we're going to have T is going to be the time, which, well, really, strictly speaking, it should then be in hours. It should then be in hours. If the speed is in miles per hour, it's safer to keep the time in hours rather than have the time in seconds. Okay, never mind, we'll carry on. And then we've got a differential equation. The car will decelerate at a rate proportional to its speed. How can we form a differential equation from that bit of information? Tell me, Sana. Yep, fantastic. Equals KV, lovely. Do you recognize this equation, Sana? It's the standard exponential decay equation. So I'm going to skip the working and I'm going to go straight to V equals V naught e to the minus kt. V equals V naught e to the minus kt. And V naught is his initial speed. So I know that he was going at 80 miles an hour. So I'm going to put in 80 miles an hour as his initial velocity. 80. 2 seconds later, his speedo reads 20 miles an hour. Okay, so, well, I want to put in T as 2, but I can't really. It's going to be 2/3600, 2 seconds. V equals 20. So if I put that information in, I can find out what K is. Once I've found out what K is, then I can work out, what do I want to work out? I want to work out when his speed reaches 5 miles an hour. So V equals 5, T equals 5. You're going to get your answer in hours, but then you might as well change it into seconds because it's going to be tiny. Okay, you finish it off. When we were doing this question, I completely omitted the bit where we solved the differential equation. I just went straight to an exponential decay equation. It's kind of cheating. You can't really do that. But it's all right. We've done so many of them today. So now I just need to put in t is 5 into this equation. So v is 5 into this equation. And then work out what t is. T will come out in hours. So you might as well multiply it by 3600 to turn it back into seconds. What'd you get as the answer, Roger?
2 seconds.
That can't be right because we've already got 2 seconds later, his speedo reaches 20. It's got to be more than 2 seconds.
I think it's
4. I see. So you got 4 and then you said, yeah, 2 more seconds. How much longer is 2 seconds? Yeah, you're right. Okay. So the final answer is 2 more seconds. So t equals 2 seconds more. So it took 2 seconds for his speed to drop to 20. It's only going to take 2 more seconds for his speed to drop to 5. You know, 5 miles an hour is the speed at which your bumper will absorb the impact. So at 5 miles an hour, you should receive no damage to your car. If you impact a wall or a barrier at 5 miles an hour, the bumper should absorb it. Okay, last bit of what we need to do today is related rates of change. So occasionally you have a rate that's the equation that you've got, the differential equation that you formed is not the one that you want. So let me just explain that to you a little bit more. When we have this differential equation here, there are 2 things I can say about this differential equation. One is the differential equation only has 2 variables, v and t. It only has 2 variables, v and t. There's a k there, but that's not a variable. It's just a constant that I don't yet know, but will shortly discover. So the differential equation should only have two variables. And in particular, this bit of the differential equation tells me that when I finish, I'm going to get an equation connecting v and t. So that bit of the differential equation tells me that when I finish, I'm going to get an equation connecting v and t. Which is great, because they asked me how much longer, which is t, until the speed is 5 miles an hour, and that's v. So if I've got an equation connecting v and t, that's very useful for the thing that I might want to do, which is calculate the time when the velocity is a certain thing. But sometimes you're going to have a rate that you don't want. Let's say, for instance, you've got dx by dt, but that's going to give you an equation for x in terms of t. But let's say you don't want x in terms of t. Let's say you want y in terms of t. Then that would be related rates of change. Related rates of change is when the rate you have in your equation is not the one you want. So you need to change that rate. And we use the want, got, need rule. So the want, got, need rule starts off with, yeah, if you want an equation connecting y and t, you have to have dy by dt in your differential equation. So that's what you want. But for some reason, you haven't got that. You've got dx by dt. You formed your differential equation and you've got dx by dt. And so you're going to need something else to convert this into this. And the thing you need is going to be, well, if you just look at the fraction, you've got a dx on the top at the moment here, but you don't want dx on the top, you want dy on the top. So that means you're going to need a dy on the top here so that you can get a dy in the answer. But then now you've got to also get rid of this dx. So you need to divide by dx. Then the dx's will cancel out and you'll be able to get dy by dt. So we need, oh, they both come together. We need dy by dx. We need dy by dx. I say we need dy by dx. It's not just going to be lying around on the side of the road for us to pick up. To get dy by dx, we'll probably need to figure out some sort of equation. We'll probably need to figure out some sort of equation connecting y and x. So let's have a go at the question. A tall 2x2 square base container is initially empty. So this is my container. And it's empty. I'm going to pour water into it from a tap. So I've got a tap here. And I'm going to pour water into it. And as I pour water into it, it's going to fill up with water. It's going to fill up with water. And the depth of the water is going to be x. But there's a hole in it. So there's a hole in it. Somewhere here, there's a bit of a hole in it. And so what's going to happen is from that hole, the water's going to drain out. And so I'm going to lose some water from the hole. So annoying, isn't it? Got a lovely container, got a hole in it. Okay, well, it's a 2x2 square base container, so that's 2 meters, and that's 2 meters. and they tell us that water from the tap is poured in at a rate of 0.08 meters cubed per second. The meters cubed per second, meters cubed is volume, seconds is time. So meters cubed per second must be dV by dt. Must be dV by dt. So this is dV by dt, and that's 0.08. But due to a hole, water leaks out at a rate of 0.12x. So because we've got a hole here, there's water leaking out at a rate of 0.12x meters cubed per second. Meters cubed is volume, seconds is time. That's also dV by dt. dV by dt equals 0.12x. That's also dV by dt. They can't be this. They can't both be dV by dt. Ah, well, look, I'm going to differentiate them. This is water flowing in, so I'm going to call that dV by dt, dV in by dt. I'm going to call that dV in by dt, and I'm going to call this one dV out by dt. One is volume in, the other is volume out. So I've just labeled them differently so you know which is which. Okay. Right. This reminds me a bit of some of the other questions we did. The one about the radioactivity and I can't remember what the other question was. I think there's another one like this. How would you, what would you say dV by dt is? V is the volume of water in here. V is the volume of water in here. V is the volume of water in the tank. And T is the time. This is in seconds, this is in meters cubed. And X is the depth of the water in the tank. And that's in meters. Just defining everything, which I'm supposed to do. So V is the volume of water in here. I've got dV in by dt is 0.08 and dV out by dt is 0.012. Incidentally, this makes sense. The water from the tap is at a constant rate. It's not changing at all. But the water leaking out depends on X, the depth of the water. That makes sense. If you have a bucket full of water with a little hole in it, water's going to run out of that hole quite quickly. But if it's almost empty, the water's hardly going to be coming out of that hole. The more full it is, that's simple physics. It's the same as the pressure-depth relationship, which tells you that if you swim to the bottom of a deep swimming pool, your head will hurt. Whereas if it's not a deep swimming pool, your head won't hurt as much. Anyway, I want to find dV by dt. Tell me what dV by dt is, Jeff? It's not, because it doesn't say anywhere here that the rate of change of volume is proportional to the volume. It doesn't say that anywhere there. This is not a proportionality one. It's nothing to do with proportionality. It's something to do with the fact that water's going in from the tap. I mean, if I put it more simply to you, you'd say, oh, that's easy, that's so obvious. If I said to you, right, imagine in the next second, 5 centimeters cubed of water comes in from here, and 8 centimeters cubed of water comes out from there. What's the change in the volume in that? It increases by 3.
Decrease.
Oh, minus 3.
Yeah, minus 3. Minus.
Okay. How did you work that? Tell me what dV by dt is, Sam. Good.
Just do 0.12x to track.
Oh, look, why did you do that? Tell him what the correct answer is then.
0.0.
Yes, this is the stuff going in, so that's positive in terms of volume of water in there. And this is the stuff going out, so it's negative. So it's simple. It's simple. All we're just doing is adding them. This one's negative, that one's positive, we're just adding them together. Okay, right. So we just formed a differential equation. It wasn't hard to form the differential equation, even though you tried to make it look as though it was hard to form the differential equation. It wasn't hard to form the differential equation. Now, tell me what's wrong with this differential equation. What is bad? What's wrong? Tell me two things that are wrong with it. Not just one, two things that are wrong with it. I hate this differential equation. Tell me two things that are wrong with it. Right.
Your variables from the rate of change when it's going to the equation. It doesn't X.
Oh, I see. So there's too many variables. There's three variables. Right. Okay. So Raja doesn't like the fact that there's three variables, which is absolutely right. You can't solve a differential equation that's in three variables. It needs to be in two variables. So we wouldn't be able to solve this anyway. That's the first thing that's wrong with it. What's the second thing that's wrong with it? And it relates to what they want us to find out, what they've asked us. How long would it take to reach a depth of 0.5 meters? Yes, you're right, Sana. You don't want dv by dt, you want dx by dt, because that will give you x and t, x in terms of t. So we're going to use the want, got, need rule. So we're going to use want equals got times need. Remind me again what we want, Sana? And what have we got at the moment? Okay, so we're going to need to adjust that by multiplying it by something. What should we multiply it by, Matthew? You're going to multiply this by something, and you want to end up with dx on the top. Dx by dv. Okay, now you can't just go around saying, I need dx by dv. Well, you can, and you do. But to find dx by dv, that's only possible if you know a rule, in other words, an equation connecting x and v. Do you know, what is v? V is the volume of the water in the can. What is x? X is the depth of the water. Is there a rule which connects the volume of the blue water with the depth? Is there some sort of equation which would allow you to work out the volume if you knew the depth of that water? Matthew? Yeah, if I tell you that the depth of the water, maybe at a particular instant, is 1.5 meters, would you be able to tell me how much water is in there? Go on then. I don't know the volume. I told you the depth is 1.5 and I've asked you what the volume is.
Oh, just x times 2 times 3.
Yeah. 4 times 1.5. So 6 would be our volume. Sorry, I didn't mean it's 1.5. I meant if it's x.
Oh, just rearrange it together.
I just want the volume. This is the depth is x. I want the volume. So volume equals 4x. Hold on, I said I wanted a rule connecting x and v, but I didn't actually. I wanted dx by dv. How am I going to figure that out now? So, Matthew, you've told me this, which is good. Lovely. So now we know dx by dv is 1 over 4 times dv by dx, or dv by dx is way up there, which is, I'll factorize it. I'll factorize out the 1 over 100 and the 4 over 100. And so that gives me 2 minus 3x. Oh, that looks a bit messy. Let me write that again. 4 over 100, 2 minus 3x, under quarter equals dx by dt. Dx by dt equals, well, that will cancel with that, and so it gives me 2 minus 3x over 100. Now this is so much better. There's no longer 3 variables in my differential equation. There is just 2. And they're the variables that I want. I wanted to have x in terms of t. So now I will just separate my variables and solve it. So 1 over 2 minus 3x dx equals 1 over 100 dt, integral, minus a third ln 2 minus 3x equals 1 over 100 t. Put a constant in here. Let's rearrange it. So ln a 2 minus 3x equals minus 3 over 100 t. E to the power both sides. 2 minus 3x equals b e to minus 3t over 100, and make x the subject. 2 minus b e to minus 3t over 100 equals 3x. 2 minus b e to minus 3t over 100 all over 3 equals x, and then fill in the last bit of unknown. The last bit of unknown is the b. It's initially empty. That means t is 0, x is 0. T equals 0, x equals 0. Slam that into the equation, x is 0, t is 0, and it gives you 0 equals 2 minus b, so b's got to be 2. So b's got to be 2. So I can replace the b with 2. B with 2. And so there's my equation. There's my equation. It's all nice and done properly. I'll just tidy it up a bit. 2/3 brackets 1 minus e to minus 3t over 100. There's my equation for x. What do they want? They want to know how long until it would take it to reach a depth of a half. So we want the depth to be a half. So we'll put in a half in x. A half in x equals 2/3 brackets 1 minus e minus 3t over 100. And then that's going to give us 3/4 equals 1 minus e to the minus 3t over 100. And that's going to give us a quarter equals e to minus 3t over 100. And that's going to give us minus 2 ln 2 equals minus 3t over 100. The minuses cancel out. And so that gives us 200 ln 2 over 3 equals t. And then stick that in the calculator just to decimal it. 0.2, yeah? 46.2, all my units, it was seconds, 46 seconds. 46 seconds it's going to take to reach a depth of 1/2 meter. So in 46 seconds, let's call that 1/2 meter, 0.5 meters. That's going to be 46 seconds it's going to take to reach that depth. As it carries on, you'll find that the depth doesn't keep on and on increasing indefinitely. If you leave the tap on in a container, the depth will keep on and on increasing until it overflows the container, until the container, and our container, for some reason, is at infinite height. I don't know how it ended up of infinite height. Accidentally made it a bit bigger than I intended to, so it's now of infinite height. If it's at infinite height, then theoretically, if we just had the tap on, it will just keep on and on filling up higher and higher and higher and higher forever. But we've got a hole in here, so it's not going to fill up higher and higher forever. Tell me how high it is going to fill up, and tell me how to figure out how high it is going to fill up. We've got water coming in here, same rate the whole time. 0.08 meters cubed every second. But we've got water flowing out here, depends on x. Depends on x. If x is 1, that'll be flowing out at 0.12 meters cubed per second. That's faster than going in. So I don't know how that's going to happen. Anyway, if x is a half, it's going to be 0.06 meters cubed a second. 0.06, and that's 0.08, that means the level will be going up. If it's going in at 0.08 and out at 0.06, that means you're gaining something. Yeah. Tell me when it will stop rising, the level will stop rising. Tell me when the level will stop rising. Bradford.
When 0.08 equals 0.12.
Yeah, perfect. Bradford says, look, if the volume coming out matches the volume coming in, if that and that match each other, then it's going to stop increasing. So in other words, 0.08 equals 0.12x, and then divide both sides by 1.12, which will give us 8/12, which will cancel down to 2/3. So when you get to 2/3 of a meter, let's say 2/3 of a meter is going to be, say, here. When you get to 2/3 of a meter, okay, here, that's it. That's as high as it's going to go. You're never going to get above that 2/3 of a meter line. And again, that same thing is evident in our differential equation. How is that also possible to identify from this differential equation? You knew it was 2/3 by looking at that. You can also tell it's 2/3 by looking at this. This equation also tells you that it's 2/3. This equation is easy to plot. If you wanted to sketch this, well, we're not plotting, sketch it. If you wanted to sketch this, you'd start off with an e to the x square. You'd start off with an e to the x bar, so it looked like that. Then you've got to squash it by 3/100. So in other words, stretch it by 33 along the x-axis. I'm not going to bother to do that because you wouldn't even be able to tell if I've done it or not done it. Then you've got to reflect it in the, y-axis. So flip it in the y-axis. So it looks like that now. This is still 1, by the way. This is still 1. Then you've got a minus here, so you've got to flip it again, but this time in the x-axis. Okay, so now it looks like that. This is now -1. Then you've got a +1 here, so you've got to shift it up by 1. Shift it up by 1. That means you're also going to shift this asymptote up by 1. So there's an asymptote here. There's an asymptote here. When you shift it up by 1, you're also going to shift the asymptote up by 1. And, oh, it's touching the asymptote. And then the last thing is the 2/3 here. The last thing is the 2/3. Is stretched by 2/3 along y. So, well, it's gonna stretch it by 2/3. That's effectively a squash, isn't it? It's a stretch of less than 1. So it's going to look a bit more like that. And instead of going up to 1, it's now only going to go up to 2/3. So that's only going to go up to 2/3. 2/3. So the asymptote of the graph would be 2/3. I mean, you don't need to sketch it to find the asymptote of the graph is 2/3. You could just say, let t tend to infinity. E to the minus infinity is going to be 0. 1 minus 0. So e to minus infinity is going to be 0. 1 minus 0 is 0. 2/3 is 1. 2/3 times 1 is 2/3. So x would, so as t tends to infinity, x would tend to 2/3. Same answer as we got by sketching it, but without having to do the sketching. Okay. a balloon is inflated. I know, such a long lesson, isn't it? Let's do that. Oh my God. That's why we did it in reverse, because I knew it's going to be too long. A balloon is inflated to 10 centimeters radius, but then starts to deflate. Initially, air escapes at 8 centimeters cubed per minute. How long until the radius reaches 2 centimeters? So we've got two ways of working this out, but we want to do it using the related rates of change method. So there is another way we could do it, but we're not going to do it that way because we want to practice related rates of change. So what we got? So here's our balloon, and what's happening is air is coming out of the balloon. And the rate at which air is coming out is, well, it says initially air escapes at a rate of 8 centimeters cubed per minute. I don't know. I'm going to have to guess. I'm going to have to make up something. Rate of air escaping is proportional to amount of air. Yeah. Does that make sense? That seems reasonable, doesn't it? When the balloons build up a lot, you're going to get it escaping quite quickly. But then as the balloon gets less inflated, it's going to be less. I mean, you might argue it wouldn't be proportional to the amount left. It would be proportional to the, not the volume left, but it would be proportional to the square of the volume left or something like that. Or you might say it would be proportional to the square root of the volume left. Or you might say it's proportional to the square of the cube root of the volume left, which probably is the best one to come up with. But we're not worried about it. We're just trying to just model it simply. We're not trying to do anything clever. So rate of air escaping minus dV by dt. Why is it dV by dt? Here we go. Air escaping. Can't you see the units are centimeters cubed per minute? It's volume divided by time. Is proportional to E equals K times the volume. Okay, so that's one way of writing the equation. If that's our equation, then that's just an exponential decay equation. We can work this out in a second. So we can just say straight away, V equals V naught e to the minus kt. Okay, so that's one way. We're not going to do it that way because, and that's one model, and that's maybe a reasonable model, but we're going to do it a slightly different model, which will involve us using related rates of change. So we're going to say rate of air escaping is proportional to the radius. That also makes sense, perhaps more sense, because the more the balloon is blown up, the bigger the radius, the more the air is going to want to escape from it, the greater the pressure of the air inside it. Okay. So we're going to say dV by dt equals kr. And now we hit the related rates of change problem. This is dV by dt, but it's in terms of r. There's three variables. And also, we don't want v in terms of t. We want r in terms of t. So what we're going to do is we're going to rewrite it. We're going to use the want, got, need rule. Want equals got times need. We want dr by dt. We've got dv by dt. So we're going to have to multiply it by something. What will we need to multiply it by? Asking that to good.
dr by dv.
Yeah. Now, where are we going to get dr by dv from? I mean, it's not exactly as if everyone knows an equation connecting the volume of a balloon with its radius. How would you even know such an equation of a volume of a balloon connected to its radius? Right here? Over 3 pi r cubed. You use the volume of a sphere, and a balloon, yeah, okay, it's not exactly spherical, but it will do as an approximation. We're only modeling here, so we're approximating it. Okay, but I didn't ask you for v, I asked you for dr by dv. Roger.
Oh, so 8/3 pi squared.
Are you differentiating like
Yeah,
dv by dr?
Yeah.
dv by dr equals, so that's going to be 4 pi r squared. But that's dv by dr.
1/4 pi squared.
R by dv equals 1 over 4 pi r squared. So we're going to replace that with 1 over 4 pi r squared. We're going to replace that with kr. Hold on, shouldn't it be minus? Yes, it should. It should be minus. Let's put a minus. Well, then let's put a minus here as well, because that's also going to be minus. Yeah, we'll put them both as minuses. Okay, so that's equal to times kr equals minus dr by dt. And so that gives us kr. Okay, so the r's are going to cancel out. So it's going to give me k over 4 pi r is dr by dt negative. Now, what I'm going to do here is I'm going to kind of merge all of these numbers together. Pi is a number I know, 3.14. 4 is a number I know, somewhere between 3.9 and 4.1. K is a number I don't know. So if you've got three numbers and you're multiplying and dividing them, but one of them is unknown, well, you don't know, it doesn't matter what the other two are, you've just got an unknown number that you're multiplying. So I'm going to merge them all into a single constant. So that's going to be minus dr by dt equals a over r. And so that gives me, separate my variables. So I want all the r's on the dr by dt side. So r minus r dr equals a dt. Integrate, integrate. And then minus a half r squared equals at plus b. Okay, what do I know? Initially, the air escapes at 8 centimeters cubed per minute. Okay, so, right, that's not really going to help me because I can't put that into here. You know what I can do? I can go back to here and I can say, look, initially the air escapes at 8 centimeters cubed per minute. So that's minus dv by dt is 8. And then I can put that in here. Minus dv by dt is 8. Minus dv by dt is 8. Is 8. Minus dv by dt is 8. Is 8 times 1 over 4 pi r squared. What was the radius initially? Oh, the radius was 10 initially. So times 1 over 4 pi, the radius was 10 squared. So that cancels down to give me 2 over 100 pi, or 1 over 50 pi. So that gives me minus dr by dt is 1 over 50 pi. So now I know minus dr by dt. So I know that minus dr by dt is 1 over 50 pi when the radius is 10 equals a over the radius is 10. And so multiply by 10, and that gives me a equals 1 over 5 pi. And so I've already figured out what a is. A is 1 over 5 pi. 1 over 5 pi. So here, not only did we have to use the related rates of change to change our original difference, we also had to use it to change the information they gave us, the numerical values they gave us. We had to change that dv by dt into a dr by dt, but we can do that because we've done it once with the equation. We can do it again with the numbers. What else do we know? We know that t equals 0, r equals 10. So r equals 10, so 100, 50 minus 50 equals, t is 0, that's going to be 0 plus b. So b is minus 50. So b is minus 50. B is minus 50. And so that gives us a half r squared equals 50 minus 1 over 5 pi times t. I might as well multiply through by 2. Let's call that 100 minus 2t over pi. And so there's our equation for r. And then they say, how long until the radius is 2? And so we just put in r is 2 into our equation and then solve it to find out what t is. The rest is easy to do. Okay. Homework is... See, I'm still skipping the last few questions, even though we spent the whole entire lesson doing those things. Homework is exercise 7.19 all. This is a tricky exercise, in case you hadn't already guessed it. So the way to do this exercise is you start it early, today or maybe tomorrow at the latest. Then what you do is, if you're stuck on a question, move on to the next question. Use the hints, try and help yourself, then move on to the next question. And then maybe on Wednesday or Thursday, you go back to it again, try a few of those again. Some of those that you couldn't do the first time around will become easy when you try it again a couple of days later. And then you try them again next Saturday. You'll find that you'll get stuck on them, but when you try them a third time, you'll be all right on them. Okay, can you leave your homework on the desk, please? And I will see you next week. Look at you, like, it's so desperate to go out there. It's like, oh, okay, right. He started talking, he's put the homework up now. We can go. It's just back up. Last one out to leave them. Leave your homework on the table. Make sure your name's on the top of it. I will see you next week. Bye.